Dear students, we are continuing our discussion on Module 6. This is the fourth video lecture. In this video lecture, we are discussing the term reliability. As we know, reliability is the probability of a device performing its functions for a period, indefinite period, in a given operating conditions. Basically, we are expecting some performance from a part, and if you are getting that performance, we are saying that that part, that or element, or that product is have high reliable. So basically for terms, basically reliability is a expression in terms of probability. Actually we are expecting that it is reliable, so it may or may not. So there's a chance is there, so it's always expressed in terms of probability, and we are expecting some sort of performance during a period and in a given operating conditions. So four terms, probability, and we need to have some performance for a given period, and fourth one, operating conditions. So what are the basic terms, or which are the important terms in reliability calculation? The first term is failure. We all know the term failure. If a function or a product is not able to perform its function or it fails, usually we are called for failure. Actually we are expected some performance from a product and it's not able to perform in a given period of condition. We are saying that that product is a failure. Okay, failure. Second one, failure rate. Number of failure per unit time. Time can be in a seconds or a cycles or a events or whatever. If you have a number of failures for a given period, for a given per item, it's called failure rate. And two new terms for you is mean time between failures. Mean time between failures usually is called MTBF. Mean time between failures. As the uh, term itself, it's the failure between two, it's a time taken between two failures. Actually, for a product, a failure is occurs, we have repaired that, then what's the time for next failure? That duration is usually called mean time between failures. Usually, mean time between failures can be calculated for repair products and non-repairable products. Okay, for non-repairable products, mean time between failure is also equal to mean time to failure. Okay, for repairable product we can repair and use it, so we are calculating mean time between failures. For non-repairable products usually we are calculating mean time to failure, that's equal to mean time between failures for non-repairable time. So it's average mean time to failure is the average time of failure occurrence. Or how do you get the difference between mean time between failures and mean time to failure? Both are almost equal, only difference is mean time between failures is a common term which can be used for repairable products and non-repairable products, but mean time to failure is only used for non-repairable products. That cases MTTF is also equal to MTBF. And why the engineering items have failed? There are many reasons, as we know that engineering items have failed. It may be due to the design issues, it may be due to the overstressed working, wear out due to time, weaker due to age, or due to any failure of any mechanism. These are some of the reasons for failure. Some other results are sneaks. What is a sneak? Sneak is the condition in which system does not work properly even though every part does. We have many examples like that. We didn't find any reason for failure, but items are fails. That issue usually called sneaks. The other options can be any errors, like maybe due to incorrect specification or due to design or due to any assembly or whatever it may be. These are the major reason for failure. Usually we have a reason for failure or reason for the reason for non-reliability, reason for lesser productivity, all are almost same. So For examination point of view, this is very important. Bathtub curve of failure. You have to study what is bathtub curve. For examination point of view, I repeat, this is very important. Bathtub curve. Look into the figure. Bathtub curve will be a graphical representation, the failures and time. Here in x-axis we are plotting time or a lifespan of a product, and y-axis we are plotting number of failures of a given product. It says that in bathtub it says that for any product there are three regions of failure. The first region, second region and third region. First region is usually called DFR, decreasing failure rate, as shown in the figure. The failure rate is decreasing. In second region, CFR, constant failure rate, and third region, IFR, increasing failure rate. Hope its figure is a shape of a bathtub. That's why it's called as the bathtub curve. In first region, failure is decreasing, then constant, then increasing. How it's happening? Hope you got the figure. In first region, failure is decreasing. Then for a given period, failure is a constant. Then when the time increases, failure rate is increasing. Three region. Usually it's called DFR, CFR or IFR. Some other term is also there. We will discuss each time. The first period, DFR, decreasing failure period, is also called early life period. Early life period. The first region where the failure rate is decreasing is called early life period. What is happening in early life period? As we know that when we are introducing a product to the market, actually that is not properly tested. Actually we are tested in a condition where we in the lab or in a factory. But in actual scenario, when a product is introduced in the market, there may be many collapse due to multiple reasons. So that is the early life period. Actually, by sorting that failure rate, we can reduce the failure rate. That's why that is decreasing failure. When we introduce the product, number of failures are more. When the time increases, failure rate decreases and become a constant. That region is usually called early life period or infant mortality phase. So, cause can be undetected hardware or software issues, or many issues can be there. After clearing all that failure, the failure rate will be constant. That is the second region, constant failure rate. That region is called steady state period. Here, for a given period, for a longer period, the failure rate is a constant. Actually, we have solved almost problems, but maybe some random cases may be there. That's why a small failure rate is there, but almost constant. So, we understood the market, we understood the major issues of product, and we have overcome that, and the product is on a normal time period, or it's going to be in a normal period. That period is called steady state period. Here the failure rate is much lower and a constant. So here the failure can be due to environmental shocks or anything can be there. And last period, what we call increasing failure period, that is called wear out period. That is due to aging. When the product life is increases, as we know that number of failure rate again goes to increases. That period is called wear out period or increasing failure period. So here, as we said, three regions: decreasing failure period, constant failure period, increasing failure period. Hope you are remembering the figure and also the three regions. Okay, so this is bathtub curve. You can expect a question, explain the bathtub curve. So draw the graph and write about three regions in detail. So next part we are discussing in this lecture is measures of reliability. I said for measuring reliability, usually we need to measure mean time between the failure or mean time to failure, and time to repair. So the first term is mean time to failure. Mean time to failure. Usually mean time to failure is measured for non-repairable products. For repairable products, mean time to failure is equal to mean time between the failure. The average time for a failure. For if a population of n items is there which having a failure time of T1, T2, T3, etc., mean time to failure equal to 1 by n total population into sigma I equal to 0 to n Ti. So it's a sum of total number of failures divided by a number of items. That is the mean time to failure. Mean time to between the failure is same that of MTTF. Same equation written in another way. Total operating time, that's the time for taken for T1, T2, T3 divided by total number of failures. And mean time to repair. How much time it takes for repair? If one failure is happening for a repairable product, how much time it taken for repair? So that is the repair time. For a population of n, total repair time divided by total number of failures. Mean time to repair. Availability. What is availability? Uptime divided by uptime plus downtime. Uptime means how much time the product is available divided by uptime plus downtime, that is total time. Okay, availability will be uptime divided by uptime plus downtime. Uptime will be mean time to failure, how much time it have, and what is downtime? Mean time to repair. So availability will be equal to MTTF divided by MTTF plus MTTR. For repairable product, MTTF equal to MTBF. So equation also can be MTBF divided by MTBF plus MTTR. And what is maintainability? Read the definition. It's a probability that a unit or system will be restored to a specific condition. How much probability is there to restore? So maintainability will be calculated using equation 1 minus e raised to t divided by MTTR. Okay, where t is the specified time to repair and MTTR is the mean time to repair. So these are the different terms. Usually all these models are used for different mathematical models. There are different mathematical models are there, either it can be a constant model, linear model, gamma model, etc. For a linear model, constant hazardous model, failure rate equal to lambda or delta, then reliability will be e raised to minus lambda t, and ft will be rt is the reliability factor equal to e raised to minus lambda t, and failure rate will be equal to 1 minus reliability. If reliability equal to e raised to minus lambda t, if failure is equal to 1 minus reliability, that is failure equal to 1 minus e raised to minus lambda t, and mean time to failure or mean time between failure is equal to 1 by lambda. We have to study this equation. For a constant failure rate lambda, reliability will be e raised to minus lambda t, ft equal to 1 minus e raised to minus lambda t, and MTTF or MTBF equal to 1 by lambda. We will do two examples for using the same equation. Read the question. It is observed that failure pattern of an electric system follows an exponential distribution with the mean time to failure is 1000 hours. Mean time to failure, as we know, mean time to failure is equal to 1 by lambda equal to 1000 hours. What is the probability of the system fail occurs within a time of 750 hours? So t equal to 750 hours. So failure at ft equal to 1 minus e raised to minus lambda t. So 1 minus e raised to minus lambda equal to 750, t equal to 1 by 1000. So probability of failure will be equal to 0.528 after solving. Very simple problem, very easy to understand and study. One more example. Read the question. A certain type of electronic component has uniform failure rate of 0.0001. So lambda equal to 0.0001. Okay. And what is the reliability? Here we need to find reliability. Reliability equation what is? E raised to minus lambda t. for a specific period of time, A equal to 10,000, B equal to 2,000. So first we need to find when T equal to 10,000 hours. Liability equal to e raised to minus lambda into 10,000, that is equal to 0.90483. Second case, B equal to 2000, so e raised to minus lambda into 2000, that is equal to 0.98. So these are the sum of the reliability calculation. In this lecture, we have discussed about reliability. In next lecture, we have discussed about the system reliability. Thank you.